Imagine it's freezing outside. Snow is falling, the wind is howling, but inside your living room, you are perfectly, comfortably warm. That warmth is provided by a hidden network. Tucked beneath the floorboards or behind the walls is a continuous loop of piping, pumping a steady stream of hot water throughout the house. How does a builder decide the exact amount of pipe needed for this specific room? If they get it wrong, the consequences are immediate. Lay down too little and you'll be shivering. Lay down too much and the room turns into a sauna, burning through energy and money. Engineers answer this question using a field of study called internal convection. This is the science of moving heat from one place to another by pushing liquids or gases through enclosed tubes. Here is a look at the basic mechanism. A pump is pushing the fluid forward through the tube. As that hot fluid travels, the heat inside it radiates through the solid walls of the pipe and escapes outward into the room. By following the rules of internal convection, builders can calculate exactly how much heat is being transferred, ensuring a comfortable room on the first try. To find the perfect pipe length, we must look closer at what's happening inside the tube. From the outside, the water might look like a single solid block sliding forward, but the movement is actually quite uneven. As the fluid flows, the physical walls of the pipe create resistance. The water touching the metal edges experiences friction, which slows it down. Meanwhile, the water in the center faces no resistance, so it moves much faster. This chart shows the result. Because of that friction, the fluid speed forms a curve, hitting its maximum velocity right in the center of the pipe. This difference in speed creates a difference in temperature. The fluid at the edges moves slower and stays in contact with the cool pipe wall longer, so it loses heat quickly. The fluid rushing down the center stays much hotter. This diagram shows the temperature imbalance. You can see how the heat drops off as you move from the hot core toward the cooler surface of the pipe wall. The thickness of the fluid determines if this flow is smooth and straight, but in most heating systems, the water moves fast enough to mix in a chaotic, tumbling motion. Because the fluid is a messy mix of different speeds and temperatures, tracking the heat of every single drop isn't realistic. The math becomes complex. Engineers handle this complexity by zooming out. Instead of tracking individual droplets, they use broad averages. The first step is calculating an average velocity. They take the slow edges and the fast center and blend them into one steady representative speed for the entire flow. Then, they calculate a second average to determine how the fluid behaves thermally, known as the bulk mean temperature. The math here is simple. You just take the temperature of the fluid entering the room, add the temperature of the fluid exiting the room, and divide by 2. This single average temperature lets builders look up the baseline properties of the fluid, like how much mass is flowing through the system every second, which leads us to the final piece of information we need, the heat transfer coefficient. This coefficient is essentially a system's efficiency rating. It's a single number that tells you how easily heat moves from the water through the pipe wall and out into your home. By relying on these averages, engineers can accurately forecast how well the heating system will perform before a single pipe is even laid. These steps form the exact process builders use to ensure a living room stays warm without using excessive amounts of material. Step 1. Use the bulk mean temperature to define the water's baseline properties. Step 2. Check the pipe diameter to determine flow resistance and see if the water is moving in a smooth or chaotic state. Step 3. Calculate the heat transfer coefficient to find the system's exact heat release efficiency rating. Step 4. Determine the total amount of heat the specific room needs to stay warm against the cold weather outside. Finally, Step 5. Since the engineer knows how much heat escapes from every inch of pipe, they divide the room's total heat requirement by that rate to find the perfect length. You can see the result in the warmth radiating up from the floorboards. A perfectly heated room is the direct result of applying the logic of internal convection to manage the movement of heat. It turns a complex physical process into a reliable, predictable system.